All right, welcome back from the Thanksgiving break. I hope you guys had a relaxing time with your family. We have 2 more weeks of classes this week and the next week, and then we'll have our final exam on December 16th. That's a Wednesday of the finals week, and I'll talk more about the final as we get closer to it. So maybe sometime later this week or even next week we can have sort of a final exam review session. Yes, Ajit, the final exam is cumulative. Okay, but when I talk about the final exam review, essentially I'm going to be focusing on what were the more important things that you guys need to focus on, because those are going to be a little bit more useful than the others going forward from here. So I'll talk more about that in a review session. Okay, let's see. We are today is Tuesday, December 1st. Homework that is due that's coming up is homework 11. That's due Friday, the coming Friday, December 4th. And then the next homework, this will essentially be your last homework 12, is going to be due the last day of class. So that's Friday, December 11th. The studio that is due tomorrow, Studio 7, the scrolling display studio. So that's coming up tomorrow. That's due tomorrow. And then the last studio for our course here, which is Studio 8, that is due December 9th. So that's the last Wednesday of the semester. Daily quiz number 23 is available on Gradescope for you guys to answer. So take a few minutes and complete that quiz. Okay, so we are moving on to the next topic here, which is finite state machine design. And my expectation is, given that we have learned about the finite state machine concepts in the previous lecture, which was essentially to go from like a design problem to a state diagram and then a state transition table, given that, and also that you guys have designed counters just before that. And when we were designing counters, we took an arbitrary sequence and we used different types of flip-flops to accomplish that counting sequence. So given these past two lectures, finite state machine design should be more or less very straightforward, because there is going to be a lot of repetition of the process. Some things are going to be slightly more interesting because some things might be new, and I'll focus more about that. But then once you get to a state transition table, the process will look very similar to what you guys have been seeing so far. So that's FSM design, and you can break down this finite state machine design into 6 steps. Now 6 steps, these are very general in nature, and it is going to be safe for you to go through each step for a given finite state machine design problem. However, in some cases, it might not be useful to do some of these initial steps. So for example, for a certain finite state machine design, obtaining an abstract specification, performing a state minimization may or may not be useful at all, or it might not apply. So these 6 steps are for in general, but for a certain problem, for a certain design problem, some initial few, like the first 3, may or may not apply, depending on the problem itself. A good way to summarize this is, if the finite state machine design tends to be very complex, then it is safer for you to go through all the 6 steps. But otherwise, if it is very simple, you may be able to skip some of these. The first problem we'll look at is the same vending machine problem. And now we are essentially not just looking at the state diagram, we are going to complete the entire design in this case. So this vending machine is supposed to deliver a package of gum after 15 cents is deposited. There is only one single coin slot that can take either dimes or nickels, and it is not going to give back any change to the user. So that's the general machine, that's the problem statement of this design. Now the step one in the 6-step process is understand the problem, which could involve drawing a picture like this. So drawing a block diagram. This may help you in some situations to understand exactly how, or to picture the vending machine and to picture what are the inputs, what are the outputs, and so on. Like I said, step one may apply in some situations, may not apply in some other situations. That depends on the problem that you're tackling. So in terms of inputs to our vending machine, we have the coin sensor, and the coin sensor is essentially going to indicate to the vending machine whether a nickel has been entered or a dime has been entered or the user has pressed reset. And then the vending machine itself is a bunch of flip-flops, so it is going to have a clock triggering those events. And then the output of that vending machine is a signal called open, which will control the gum release mechanism. On the left we have the inputs, and on the right we have the one output. So by drawing a picture, it might help you understand the problem a little bit better. That's step one. Step two is map into more suitable abstract representation, meaning you can start off with tabulating all the typical input sequences. How would a user go about operating this vending machine? Well, to begin with, you might hit reset. You come to some state 0. And from there, the user might put in 3 nickels to get the pack of gum. So that would be go from here to here, and then go from here to here, and then go from here to here, and you reach S7, and that opens. So open is within that state, right? So that's, let me highlight this, open right there. So that would open your vending machine, the gum release mechanism. Now, as soon as you see this state diagram on the right, you should be able to comment about what type of finite state machine this is, Mealy or Moore. Moore is absolutely right. Because as you can see, the output open is associated with the state, and it is not associated with the arc, the arrows. So that's the way you can determine whether it is a Moore machine or Mealy machine. All right, so that's one way, that's one typical input sequence. And similarly, you can go through all the others, right? First enter a nickel and then a dime. That will also get you to 15. So that would be get a nickel and then get a dime, and then that would be S4, and then you can also open over there. In the same manner, the user could have done dime and nickel, or 2 dimes, or 2 nickels and a dime, resulting in how many states do we have here? The last state is S8. The first state is S0. So if you tabulated all those input sequences, you will end up with 9 different states here. S0 all the way to S9. And we know that if you have 9 states, when you do the encoding for the states, you will need 4 bits to do this, because 3 bits is not going to be enough. And if you need 4 bits to encode all the states, you would need 4 flip-flops to get this done. And clearly, we can do better than this. We can do this same problem with fewer number of states. And if you think back to our previous lecture, we just dealt with this with 4 states, in which we did not look at the typical sequence. We looked at the amount of money that the vending machine has: 0, 5, 10, and 15, and done. So that was 4 states, 2 bits to encode, which means 2 flip-flops were going to be enough, right? So that's your next step. After you map into more suitable abstract representation, then you go into state minimization. State minimization tends to be the most kind of difficult step in this 6-step process, because this needs you to be a little bit more creative and think a little bit, not in a structured manner. There's no formula to do the state minimization. You would have to think about how you could reuse the states wherever possible. And your goal is, I want to have as less states as possible so that I can use fewer number of flip-flops to encode those states. And over here, we have another Moore machine state diagram on the left, doing the same vending machine. It's the same vending machine as before. So 0, 5, 10, 15, and when you reach 15, you open the machine. Still your inputs are nickels and dimes, and there is a reset to start things off. All of them are the same. The difference is, in the previous state diagram that we saw, we had 9 states and we were going through this not in a very efficient manner. We were not reusing states. But over here, you have essentially have one state in which we open. So we have reused the states because now we are associating the state assignment to the amount of money it has, not necessarily for the sequence or the typical sequence. So that's our vending machine state diagram. Once we have this minimized state diagram, once you are here, then after that it is going to be very straightforward to go through the rest of the steps, because they are going to look very similar to your previous 2 lectures in counter design and FSM concepts. So from here we have a table, the symbolic state transition table or symbolic state table. Symbolic, which means I still have symbols for present states and next state. All of these are symbols. So present state could be 0 cents, 5 cents, 10 cents, 15 cents. And from each present state, you could have 2 inputs, right? If you are in 0 cents, you could not get a nickel, not get a dime. In that case, you stay in that 0 cents state, and the output is not to open. And then similarly, if you are in 0 cents and you get a nickel, then you go to the state called 5 cents and you still don't open. The third one, if you are in 0 cents, you get a dime, you go to 10 cents, still don't open. And then the last one here is present state is 0 cents. What happens when you enter here? Here is the question for you guys. If this is a 1 and this is a 1, why is this not 15 cents? Should I write 15 cents here or a don't care over there? Why is it don't care? You guys are right. It is only a single slot. So there is not a possibility for the user to enter the dime and the nickel at the same time. You guys are absolutely right. So that's going to be a don't care situation, and the output is also don't care. And in the same manner, from each state, you would have four cases, 4 inputs, and you would fill out, you would go through, look at the state diagram and fill in your symbolic state table. From when you go to the state when you have 15 cents, the only way to get out of this state is to hit reset button. Until we hit a reset button, we are not going to be able to go back to our initial state. So if you keep putting nickels and dimes, it is just going to be in that state, which means that once the gum release mechanism has been activated, it is just going to be like, it's going to keep taking all your money no matter how much you put in beyond that. There's a question on the chat box. So output open is only active when present state is 15 cents. Yes, you guys are right. This is the only time when I am in this state, that's when it's going to be active. Yes. All right, so state diagram to symbolic state table. Once you have the symbolic state table, the next step is going to be to go from symbolic to encoded state table. And how do you go from symbolic to encoded? Well, we simply have to do a state assignment or state encoding. Now, the state encoding that we have done over here is, we said, let's have 0 cents as 0, 0, and 5 cents as 0, 1, and 10 cents encoded as 1, 0, and then 15 cents encoded as 1, 1. And all of these things have been adjusted. So this state assignment steps have been adjusted over here and over here. The inputs column and the output column is still the same, but we have essentially changed our 0, 5, 10, and 15 from earlier to a state encoding. 0, 0, 0, 1, 1, 0, 1, 1. Do I have to do it this way, or could I have done it slightly differently? Like, do I have to say 0 cents is 0, 0? Could I have used 1, 1 for this? You can do it however you want, and absolutely that's the right answer. State encoding is a user's choice. They all have to be different states, but that state assignment is arbitrary. It's a user choice. I've just chosen the more straightforward one, 0, 0, 0, 1, 1, 0, 1, 1. But that's absolutely up to the user. Now, the next question we are going to try to answer is, how many flip-flops do we need for this? And this is kind of very clear once you see this state encoded table, because what we have is Q0 and Q1, the outputs of the flip-flops. D0 and D1, those are the inputs of the flip-flops. So obviously we have two flip-flops, which is the same way of saying log base 2 to the number of states. I actually should be putting another, it is the ceiling operation for this, right? So let's put a ceiling operator here. That's it. So we had 4 states, log 4 to the base 2, we got 2. But in some cases, you might need to do a rounding up, like a ceiling operation to the next integer. So for that, I've included those ceiling operators on the sides here. Okay, next. I have the present state, I have the input, I have the next state column, and I have the output. My next step should be to write the equations for D1, D0, and open. I'm going to need to write logic expressions for these 3 in terms of Q1, Q0, D, and N. So that's my next step. And before we actually do that step, can you guys tell me how many K-maps would I need to draw, and what is the size of those K-maps? President says 4 K-maps and the size is 2 by 4. 2 by 4? Okay, so here, let us talk about how many K-maps would you need. Well, it depends on how many outputs you have, right? How many outputs how many things I need to write an expression for? I need to write an expression for D1, D0, and open. So I would have 3 K-maps. You guys see that? I would need 3 K-maps because I have 3 things for which I need to write logic expression. Next, let us come to the size. Yes, 4 variable. You are absolutely right there. So we need a 4 variable K-map because we have 4 of these guys. So that's the next step. Write logic expression, or you can say write the simplest logic expressions for D1, D0 open in terms of Q1, Q0, D, and N. Those happen to be our present state and inputs. So you are going to result with 3 K-maps, each K-map being a 4 variable K-map. Time consuming, but fairly easy to go through. And D flip-flop is going to be the easiest to use because Q plus equals D. So that step is going to be very easy to complete. Now I'm just writing this statement with respect to how easy or tough it would be to fill out the state transition table, the encoded state transition table. This is not necessarily indicating that it is going to be the cheapest in terms of logic gates being used to implement. This is just for the sake of the easiness of filling out a table like this. Because when you have next state using D flip-flops, then all you have to do is the next state is your D, which is why instead of writing Q1 plus here, we just wrote D1 because they were the same. All right. So what you would do, you would go back and take a look at those that state transition table. You would enter it into a K-map for D1, K-map for D0, and a K-map for open in terms of your present states and your 2 inputs, dime and nickel. You would put it in the 4 K-maps, and then you would write don't cares wherever there's a don't care, zeros or ones, and then you would start writing the simplest SOP expressions for D1, D0, and open. Again, this is going to be a little bit time consuming, but I hope that it is going to be very, very straightforward for you guys to complete this step. Once you do that, you will get 3 equations. Equation number 1 for D1, equation number 2 for D0, and equation number 3 for open. Once you have these equations, then we are going to complete our last step here, which is step 6, which is to essentially draw out our vending machine finite state machine. Now the question is, where do you start, right? And the way I would start is, I would first notice how many flip-flops do I have? Well, clearly I have 2 flip-flops. The inputs of those flip-flops are D1 and D0. And the outputs of those flip-flops are Q1 and Q0. So I would sketch out 2 D flip-flops and I would name them flip-flop 1 and flip-flop 0. And I'm using the numbering scheme of 0 and 1 just so that there is a differentiation between D1, Q1, D0, Q0, and those two columns for present state and next state. That's step 1. Draw how many ever flip-flops you need. The next step that I would do is I would look at these equations and then I would try to implement those equations on top of my flip-flops. So for example, D1 equals Q1 or D or Q0N. So D1, that's right there, that's the input to the D flip-flop, equals Q1, so that's right there, this is your OR gate, there is D, so that's your D, that's the dime dime input that is coming from the coin sensor. And then the last one is Q0 and N. Q0 is essentially coming from right here, the output of the second flip-flop, or I should say flip-flop 0. So that is essentially the same as that. And then there is N, which is the nickel input from the coin sensor. So you have Q0 and N, or D, or Q1, which is essentially coming from here. So essentially imagine that there is a feedback wire there. And also there is a wire between here and here. And similarly, there is a wire between here and here, and so on. You guys get the idea. All of those things we did not draw just because it would have been very, very difficult to look at. All right, so there's a question in the chat box. Let me get to that. Is there some way to high voltage charge the whole system and or you could just shake it enough to get the 15 cents. That's funny. All right. So once you do this, the next step is, similar. The input of D0 is coming from all of these things. So you would have the appropriate logic gates. You would connect it to the appropriate inputs. Some of them might be coming from the output of the flip-flop. Some of them might be the complement of the output of the flip-flop, and so on. And you would give all of that to the input D0 over there. Last step, open equals Q1 and Q0. That's very simple to do. Q1 comes from here, Q0 comes from here. It goes through an AND gate, and that will be your signal open. And that, so you also have a clock for these guys. It's an active, negative edge triggered flip-flop here that we are using. But we are going to use, essentially the clock is going to be much faster than the user entering the nickels and dimes. So it's not going to play a big role in terms of our vending machine problem. It's much faster, so we don't need to worry about that. What is the slash? That's the NOT. Let's go back. Can you briefly go back to step 4 for 1 second? Sure. Step 4 is right here. Yeah. So this is state encoding, right? And the only thing that we are doing here is we look at our symbolic state table and we simply replace these symbols, 0 cents, 5 cents, 10 cents, 15 cents, with a state encoded bit pattern. All right, brilliant. Now, you might wonder, what if we start using different types of flip-flops? So here we are going to design the same vending machine, but we are going to consider a JK flip-flop for this. We still need 2 flip-flops because we have 4 states. Still need to do that. However, we, instead of having, so earlier we had what? Present state, inputs, then we go, our next state and the D flip-flop inputs were the same column. And the last one was output. But in this case, because we have a JK flip-flop, we would need to look at the present state and the next state. So think about this. The present state needs to transition to the next state. So present state needs to go to the next state. And for that, I need to provide a particular excitation. So we would need to look at the excitation tables for JK flip-flops in order to fill these 4 columns. right? Excitation tables. So look up JK excitation table. The present states column has not changed. We still need two flip-flops. Our inputs column has not changed. Our next state columns has not changed, but we have simply removed the D columns and we have included J1, K1 for flip-flop 1, J0, K0 for flip-flop 0. And if you are comfortable with excitation tables, this should be pretty straightforward lookup, right? So 0, 0 needs to go to 0, 0. Sorry, let me do this step by step. 0 for Q1 needs to go to 0 for Q1 plus. That is why I need to give 0x for J1, K1. And in the same way, you would look at 0, right? Q0 is 0 here, Q0 plus is 0 there. So I need to provide 0x for J0 and K0. That's from the lookup, the excitation table. And you would essentially do that for all the 16 rows over here to complete that. You would look at Q1, you would look at Q1 plus, figure out J1, K1. You would look at Q0, you would look at Q0 plus, figure out J0, K0. And you would keep doing that process for all the 16 rows. There is a particular column that is missing here. Which column is missing from this state transition table? Oh, no, the column, the full column. So there's a column from present state. Yes, absolutely. Output. So there is no column for output over here because output depends on, because it's a Moore machine, right? So if you have a Moore machine, your output depends on present state. That's it, right? So our present state is not changing. So even if you change the flip-flops that you are using to implement the vending machine, the output open is not going to change. So it's going to remain as is, right? It's going to remain the same. And in fact, I don't even need to do this again. I can simply take the expression here and use that instead. So that open is still going to be Q1 and Q0. That will not change. I don't need to worry about that. Now, let us do this. How many flip-flops do I need? For what outputs do I need to write those expressions? And what is the size of the variable K-maps? So let's start with logic expressions for and then number of K-maps and then size of K-maps. We would write logic expressions for five K-maps, 4 variable K-maps. All right. So 5, let us see. You would be writing expressions for J1, K1, J0, K0, and I suppose I already have the expression, but open. So that's 5 variables. Perfect. That's correct answer. Now how many K-maps? Well, I have 5 logic expressions, so I would need 5 K-maps. The next step is size of K-map. Well, that depends on the inputs. Present state has 2 and inputs has 2. So that would be 4. So that would be 4 variable. So we have 5 4 variable K-maps. And once we understand that, this step is going to be quite simple to complete because it's going to be repetitive. time consuming. However, it is going to be straightforward, just time consuming, right? So we have 4 of the K-maps shown over here. I don't need to worry about the K-map for open because we already did that, and open is simply Q1 and Q0, so that's nothing to worry about. So our 5th K-map is not being shown here just because we already did that earlier. So from the K-maps, you would get equations for J1, K1, J0, K0, and open. And once you have those equations, you would put in the logic gates appropriately to go into the J and K inputs for the vending machine. Just as we did with the D flip-flop, now we have JK flip-flops. Now, if you compare the previous implementation to this implementation, it looks like when you use JK flip-flops, you have 1, 2, 3, 4, 5, 6, and 7 logic gates that are being used. However, when we did this with a D flip-flop, we had 1, 2, 3, 4, 5, 6, 7, and 8 logic gates, right? So this tells me that the choice of the flip-flop controls the cost of the implementation. So in some cases, D flip-flops might be cheapest. In some cases, JK flip-flop is cheapest. In some cases, T flip-flops is cheapest. So how do I differentiate between all these things? Well, the way I look at things is this. If you have counters, we saw that T flip-flops, the toggle flip-flops, are very useful for designing counters because there is a toggling characteristic that is inbuilt into counters. So toggle T flip-flop suits that the best. If you need to have a very simple or a fast process to do it, like you don't care about the number of gates, you just need to fill out the state transition table quickly, then D flip-flops would be the best because of a very simple characteristic equation. However, in general, if you had to choose a flip-flop without knowing the cost, then JK flip-flop suits most applications the best. So in general, JK flip-flop, for ease of use and for registers, you would use data flip-flop, D flip-flop, and for counters, you would use toggle flip-flop. So that's kind of like a summary about how you would go about choosing the flip-flops. All right, so we have taken a look at that. Now, the next example that we are going to look at is a complex counter. And it's a 3-bit counter, and it has one input bit. That input bit is called mode M. And when mode M is 0, the counter is supposed to count in the normal sequence, which is 0, 1, 2, 3, 4, 5, 6, 7, and back to 0 and so on, when M is 0. So M is your mode. But when M is 1, we want our complex counter to count in gray code, meaning only one bit can change at a time with respect to the next bit, next number. So 0 to 1 to 3 to 2 to 6 to 7 to 5 to 4, and then back to 0. And as you can see, there's only one number or only one bit that changes from any two sequences. So if you see this guy changes, and so on. You guys can take a look at that. So when mode is 0, you count in binary. When mode is 1, you count in gray. That's the complex counter that we are going to design. Now in this case, you don't need to draw a diagram. You can skip some of the steps and you can straight go to the state diagram. Now the state diagram is, you have all these states. You have 8 states. 8 states representing the 8 states of the complex counter. It's a 3-bit counter, so you are going to have 8 states. S0 all the way to S7. So that's 8 states. Now, When m is 0, you are supposed to count in binary. So when m is 0, you go here, 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 and here. So that's a very straightforward counting process. You go from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 0 to 7, and then back to 0, and so on. Right? From here, you go back. So that's your straightforward counter. However, when m is 1, you are going to have go 1 here, go 3, from here you go to 2, and then you go to 6, and you go to 7, and then you go to 5, and then you go to 4, and then you go back to 0. So that's counting in gray code. First, sketch out all the circles, denote the states, indicate the outputs of the flip-flops in those states. Again, we have a Moore design over here, right? The output of the state is associated, the output is associated with the state itself. And then you would sketch out all the arcs, add the appropriate arcs, all of them for 0, m is 0, and then the next ones for when m is 1. Once you get to the state diagram, things will be straightforward, because after this there will be a state transition table, right? State transition table will be what? Present state, input is just m, and then next state, and then output. We don't need to even talk about the output, because there is no other output except for the outputs of the flip-flops. The outputs of the flip-flops are the counter value. So that's essentially present state. So in terms of present state, what do you have? You have S0 all the way to S7. So you're going to have what? Q2, Q1, Q0, 3 bits to encode that. Then you have M. You would do that for M is 0. You would do that for M is 1. And then you would write Q2 plus and Q1 plus and Q0 plus when m is 0, and then for when m is 1, right? So you would do, like, you would have 8 rows for m is 0, and then you would have 8 rows for when m is 1. So in total you still have 16 in this case as well. And then output is essentially present state. We don't need to worry about that, because Q2, Q1, Q0, those are the value of the counter. You guys see how to do this? Now, if you were asked to implement this with D flip-flops, then you would say, I need D2, D1, D0, and D2, D1, D0 equals Q2 plus, Q1 plus, Q0 plus, and that's it. You would write the K-maps and equations, and you would sketch it out. But if you were asked to implement this with JK flip-flops, then you would write J2, K2, and then J1, K1, and J0, K0. Look up the excitation tables. Look at how is the present state going to the next state, for what sort of inputs it's going to go to the next state, and then fill out those columns. So I hope this process is simple, straightforward for you guys. Again, time consuming, but not necessarily difficult. Questions about this example of complex counter? Okay, let us do slightly something different. What we have in the next example is a combinational lock with two inputs, x1 and x2. So lock has two inputs, x1 and x2, and when the user presses x1, then x2, then x2, that's what opens the combinational lock. Now, to simplify things, we are going to assume that only one input per clock is entered, otherwise we time out. In this case, we are going to start looking at what are the states we need to look at. So I'm going to say when we start our finite state machine, let's just say our starting state is A. And then once we get x1, we will call that state B. And when we get x1, x2, when we get x1 followed by, then we get x2, we are going to call that state C. Got x1, then x2, then x2, then that we are going to call state D. So I'm essentially using the state name A, B, C, D. I could have used S0, S1, S2, S3, but A, B, C, D is simpler. State name A, B, C, D is being used to indicate how I ideally want to progress towards opening the combinational lock. Why are there two x2s for state D? Oh, because that's what opens the lock, right? So there are two inputs, x1 and x2, and only when the input and the user enters x1, then x2, then x2, you open the lock. Otherwise, you don't open the lock. So it has to do with what is desired. Like if you want to open the lock, you got to enter x1, then you got to enter x2, then you got to enter x2. You see, in this one, I did not assign a name to a state. I don't even have the state got x2, right? Why is there got x2 not there? Why is it absent from this? So can the user input any string of inputs followed by the password to unlock since there is no error state? Yes. In a simple combinational lock like this, yes. So all the user has to do is press it enough number of times that they get lucky, right? So it's a 3-bit sequence. So if they just tried arbitrary sequences, they will hit x1, x2, x2 eventually, and you will get it, right? But this is a simple combination lock. The combination lock that we will eventually design will have an alarm. There will be a sequence to come out of the alarm, and they will, so a lot more functionality, right? So that's where we are going. But to do that, we also need this. So this is simple. Yeah, you are right. The user can randomly press buttons and get lucky. That's fine. We are not protecting our lock too much in this example. Coming back to the question, why don't I have a state called got x2? Ian says it doesn't help you unlock the lock. Yes, it doesn't. So which state is this the same as? Isn't that the same as starting state? It's absolutely the same as starting state, right? I'm not going to have a state which is not being used in my opening of the lock sequence. Got x2 is the same as start. So if you press reset, you go into state A. From state A, if the user presses x2 first, you stay there. You don't go anywhere. But if the user presses x1, then you go to state B. All right, let us look at more details about this combination lock. So let's take a look at how is that assignment going to be made. So all the way on the left, I have the meaning of the state and the name of the state, just as we had before. So those things are exactly the way we had before. Start, got x1, got x1, x2, got x1, x2, x2. State A, B, C, and D. Now let's go through this. These columns are for x1 and x2. So this essentially means x1 is 0. This means x2 is 0. x1 is 0. x2 is 1. And so on. And that is per clock cycle. So there is a timeout as well, right? So if you time out, you go back to state A. That's an assumption that I'm making. If the user doesn't press any button and the finite state machine times out, you go back to state A. So don't press X1, don't press X2, and you time out, you go back to state A. As you can see, if your starting state is A or B or C or D, if you do not press X1 or X2, then you time out and you go back to your initial state, state A. I hope you guys see that. Is my thing stuck? Is it improving you guys, or is it the same? Improved a little bit. Video quality dropped for me. It's a little bit better. Okay. All right, I'm going to be right back, you guys. I need to see what the issue is. All right. Let us push on. Is the sound quality okay? All right. Okay. Let's continue. The video, even if it is not very crisp, the good thing is that I can zoom in and out on it. So let me know if something is absolutely not being seen clearly. So I'm talking about what happens when you don't press any button, right? X1 is 0, X2 is 0. You time out and you stay in the initial state, state A. If you are in state A, which is the starting state, and you press X2, then you remain in starting state A. That's what we said earlier. Got X2 should be the same as start. But if you are in A and you press X1, you go to state B. That means you got X1. But if you are in state A and you try to press both buttons at the same time, then two things can happen. Because this is the user hitting the buttons at the same time, one possibility is X1 could get counted. The other possibility is X2 could get counted. Because it is impossible for a human to press both exactly at the same time. So the way we look at this is, even though they are coming at the same time, only one of them might be getting counted to begin with. So if X2 gets counted, then we are in state A, just as this. And if X1 gets counted, then we are probably going to state B. So over here we have this ambiguity about what would happen when the user hits both the buttons simultaneously. You could go into state A, you could go into state B. But I have a way to deal with this. As a designer, I could force this to be A. I could change that, remove all the ambiguity and say, If you try to press buttons at the same time, 1, 1, I'm going to force you to go to reset state. A, all four. So that's the way we could deal with this both buttons getting hit simultaneously later on. But that also happens here, that also happens here, that also happens over here. And I'll talk about that. So do you unlock in state A or in the starting state? You don't unlock. The only time you unlock is when you are in state D, after the user enters the 3 buttons, X1 followed by X2 followed by X2. Only then you unlock. Now let's talk about got X1. If you are in got X1 state, that is, the name is B, don't get anything, you time out. You get X2, that means you got X1, then you got X2, so you go to state C. You get X1, so that is like saying got X1, then you got X1 again. That means you entered the wrong sequence. The wrong sequence is go back to state A. So some protection is inbuilt in this, right? We are not going to state B, we are going to state A because the user has entered 2 X1s in the same simultaneously. No, sorry, one after the other. So we are not going to state B here. When there is ambiguity, again, either this guy might be getting counted or this guy might be getting counted. So we have this ambiguity over here. Again, we can deal with that by forcing it to be just A. We don't unlock in state B because we just got X1. Now next, let us move on to state C here, which is got X1, then we got X2. From state C, don't get anything, you time out. If you get X2, that means you got X1, you got X2, and then you got X2 again, so you go to state D, where you can unlock. Got X1, got X2, then you got X1, wrong sequence, you go back to the starting state. Ambiguity, it could be either A, could be either D, and we can deal with that by forcing it to be A. Still don't unlock. The last is over here, you got X1, then X2, then X2, that is state D. What would happen next? If you don't press anything, you reset. You go back to A. However, from here, if you press X2, then because earlier you could have reached D from here, there is an ambiguity here. You could have reached D from there. I should say this. You could have reached D because of that earlier ambiguity from state C. So again, this new X2 could create that ambiguity, A or D. We can again force it to be A. But once you get X2, then X2, then X2, then you get X1, that should get counted as opening the lock again. Got X1. From D, if you try to press both buttons at the same time, then you reset. But when you are in state D, you unlock. So from this example, one, we look at some ambiguities that could happen when there is a case of hitting buttons at the same time. And the way you deal with that is by adjusting the state table to force one or the other, as opposed to leaving it ambiguous. So in the next case, we can just say, all right, we are going to have A, B, C, and D assigned. We have 4 states, so I can use 0, 0, 0, 1, 1, 0, 1, 1 to assign. That's my state assignment here. So if, eventually I will get 2 flip-flops in this case, right? Because I've got 4 states. But state A, I'm using 0, 0. State B, I'm using 0, 1. State C, I'm using 1, 0. D, I'm using 1, 1. And now I'm also going to include, so state A, I have state name, I have replaced with Q1 and Q2. You can also call it Q1 and Q0 or Q, it doesn't really matter. Q1 and Q2 are outputs of the flip-flop. indicating the states A, B, C, and D. And then based on our state encoded table, we have also adjusted A, B, and C, and D in all these 4 columns. For example, all of this is A. Again, when there is ambiguity, we have also replaced that with all A's over here. We have removed that ambiguity. We are forcing it to be going to the start state, and we only unlock in state D. So once we have this is the encoded state transition table. So once we have the uncoded state transition table, then we can go into writing the logic expressions for Q1 plus and Q2 plus in terms of Q1, Q2 and the inputs X1, X2. And then you will even also write an expression for unlock. You will draw the 2D flip-flops or whichever flip-flops you want to use here. So all of those steps are exactly going to be the same as before. The critical step is to come to this. Once you arrive at the encoded state transition table for your particular state assignment, from there it will be about K-maps and logic expressions and drawing out the state machine. So that's that. So all of this is just left blank here because you can figure this out once you complete the K-map process. So the main difference from last example is that, yes, you're right. So the only difference here is the ambiguity and how you deal with that. So again, it has to do with the user saying, okay, I'm going to force it to go back to restart, or I'm going to let this be ambiguous. So however the user wants to deal with it. But also there is the main difference is that, however, there's a subtle difference about going from a vending machine to pushing buttons to open a lock. Okay, so that would complete that. Again, because we are using flip-flops, we need to worry about the setup and hold times. Things cannot change too fast with respect to one another. Inputs need to be stable before the clocking events happen. And if you have a situation where the humans are interacting with this, then you can rely on the slowness of user inputs, that they are going to be stable before the clocking event, which is typically very, very, very small. We also need to worry about the propagation delay, because there is going to be propagation delay through the flip-flops. One thing that you need to note is, if you have asynchronous signals, the way we have it for melee machines, then they can take effect immediately. But if you have synchronous signals, like the outputs of the Moore finite state machines, then they take effect at the next clocking event. They don't take effect immediately. They wait for the next state to become present state, and then that's when the signals will take effect. All right. No, we've done this. Right, we can do this quickly. So this is a slightly different deposit return machine. So I'm gonna kind of go through this a little bit quickly, so stay with me here. There is a machine that returns 5 cents deposit on a container. So the user returns a container, and then the machine gives the user 5 cents back. For every 5 containers returned, the machine dispenses a quarter. So the user enters 5 containers, gets back a quarter. If the user has less than 5 containers credit, when the user presses done, the machine dispenses the correct number of nickels. So for example, if the user has 4 containers and the user gives the machine the 4 containers and then presses the input called done, then the machine will dispense 4 nickels. If the done button is pressed with no containers, then obviously no coins are dispensed. So you can't cheat this return machine. All the outputs should stay on until the done button is pressed or a container is inserted. So the the outputs are going to change only based on the container or the done button being pressed. That's when the transition is happening. So that's our specifications for this finite state machine. From this, we can complete step number 1 as shown here. We have inputs and outputs. The CAN input sensor is going to indicate the count. I got 1 container, I got 2 container, and so on. The user, whenever they are done putting in the containers, they can press the input done to expect some money back. There is a reset to start things off, and then there is a clock to trigger the flip-flops inside the deposit return machine. The outputs are 2 forms. There is 5 cents and there is also a quarter. The quarter is only for the case where the input is all 5 containers that are entered. So when you get a quarter when you put in 5 containers. But you get 5 cents when you enter maybe 2 containers or 3 containers and then press done. So that's our block diagram. Then we go on to step 2, which is to map into more suitable abstract representations. So for example, the typical input sequences could be 0 cans and then you press done, you get nothing. 1 can, you press done. 2 cans entered, then press done. 3 cans entered, then press done. 4 cans entered, then press done. 5 cans entered and then you pressed done, or 5 cans entered and then you automatically get a quarter back, and then you go back to the first state, 0 cans entered. Now the assumption that we are making over here is that the can sensor input and the done button cannot be asserted at the same time. So you would have to press the done button after the can has been entered, or before, but it cannot happen at the same time. So what I wanted to really get to is this state diagram, and it might be looking very, very complex here, but in reality, it is not that complex. We'll break it down. So let's start with what is the meaning of C and what is the meaning of D. So C is indicative of the can input. C is standing for can input. And D is for the done button. So for example, how do you start things off? Well, you start things off over here, state 0. You hit reset button and you are over here. You don't have any money credited to you, and you have not, because you have not entered any can. When you enter a can, you go here. You enter, so notice over here, this is not 5 cents in state 1. The user would have to hit a done button to go to state 9. That's what it gives you 5 cents back, and then you come back over here no matter what. So the dash over here is indicating that essentially we are timing out. So let's see how we can get to state 5. So from 0 cents, enter the user presses inputs a can. You go to state 1. Second can, third can, fourth can, and then fifth can. Once you go to fifth can, automatically you get a quarter. However, if you either press the done button here, or you do not put in any coin or done button, you go back to the original state. So that is essentially saying if you don't do anything from here, you go back to the original state after dispensing the quarter. Now let's take a look at what would happen if you entered a entered a can from this state. If you entered a can from this state, you go back to the machine having one can. From each state, 0, 1, 2, 3, 4, if you do not give it any, well, if you put in done button here, you stay there, right? You don't give anything. But if you don't do anything from state 1, for example, you stay there. If you don't give anything from here, stay there. Nothing, stay there. Nothing, stay there. So that dashed is saying you're not doing anything there, can or done. You're not doing any of those. Do you not get the 25 cents? Yeah, you get 25 cents here. The only way to get 25 cents is to enter all the 5 cans. But if you press any, like if you stop at 4, you cannot get a quarter. You will get, so you see, if you stop at 4, how does that look like? 1, 2, 3, 4, and then when you press done, what do you get? You get a 5 cents there, 5 cents there, 5 cents there, 5 cents there, right? So you get 20 cents there. So the blue highlighted path is showing you how you can get 4 cans in and 20 cents out. What happens if you hit done or add a can when you are at state 6, 7, 8, or 9? So 6, 7, 8, 9, you are not accepting any input. You are just going through that very quickly without having to wait for that. So that is why we said we are going to have that can and the done pressed. You need to separate them out in time. So this one is happening fairly quickly after the user presses done, right? So you get to state 6 or 7 or 8 or 9 only after the user presses a done button. If you add a can at state 5, there is no output. Yeah, so if you add a can to state 5, you go back over here after dispensing a quarter, right? So this is the output there. It has dispensed a quarter and then it is looking at the next can you entered and it is counting that as one can. All right, so I hope that you guys are okay with this state diagram. The idea is as you are entering more and more cans, you progress in this way, and as you press done from any of those states, you go back like this. Once we have the state diagram, you can take this to your state transition table and then logic expressions and sketch all of that. And we don't need to do that for every example. Let me just ask you, how many flip-flops do you think this design will have? At the end, if you had to do this all like completely, at the end, Zach says, I'm going to have 4 flip-flops, and he's absolutely right. Yeah, absolutely right, you guys. So you have 10 states. If state 5, if we do not do anything, it will go to state 1, right? If you do not do anything from state 5, you go here. State 0. All right, let's see. Yeah, 4 flip-flops is absolutely right. Next. So all those steps are mentioned over here. There is present state inputs, next state outputs, and we have present state going from 0 all the way to 9. From each present state, we are looking at a done button and can input. We are looking at 4 input combinations from each present state as our starting state, and we are looking at the corresponding outputs, 5 cents or 25 cents. So this is a symbolic state table And you can also go into an encoded table by just saying present state 0 is encoded as 0000, and then 1 is encoded as 0001, and so on. But that would lead to a very, 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 9, right? 9 times 4. Well, over here we don't have much to do, but you have a lot of combinations to deal with, which means that you are going to have a very, very big state encoded table. So once you do that, this is just showing you the state encoding. State 0 is 0000, 1 is that, and so on. Again, arbitrary choice, but you will need 4 flip-flops. But if you complete all of that, you will get these expressions for a D flip-flop implementation. And those, when you actually put that all into a schematic, the implementation will look like this. So of course we are not going to spend time looking at things which are time consuming, but not too nothing new here, right? Like it's all K-maps, equations, and all of that. So what is the crucial step? Again, the crucial step is this right here. Once you are at the state diagram and you have completed the state diagram, after that your procedure of the steps, step 3, 4, 5, and 6 will be straightforward. Time consuming, but nothing too difficult. All right, so let's move on here to a finite string recognizer. Actually, are you guys game for completing this finite string recognizer? What do you guys think? Or you guys want to stop here? Okay, I'm going to stop here